In this video, let's talk about theorem 2. So in our previous video, we spoke about dot product with its properties and theorems, where we spoke about the first theorem. So in this video, we will talk about the theorem 2. So theorem 2, we have two vectors A and B. Two vectors A and B are orthogonal if and only if A dot B is equal to 0. So orthogonal is the same as perpendicular. So orthogonal or perpendicular. So we have an example here. So example, show that 2i plus 2j minus k is perpendicular to 5i minus 4j plus 2k. So how do we do it? So with this question, you just remember this theorem. So two vectors A and B are orthogonal if and only if A dot A is equal to 0. So with this one, we just have to solve it, try to do the dot product of that and see if you get 0. If you get 0, then it is perpendicular. So let's do it. So you can try to pause the video and try to do it and see if you can do it. So with this, we have 2i plus 2j minus k. The dot product of 5i minus 4j plus 2k. So when we do it, we should get 2 multiplying 5 plus 2 multiplying minus 4 plus minus 1 multiplying 2. And this should give you 10. This should give you negative 8. And this should give you negative 2. And when we add it, we should get 0. Therefore, 2i plus 2j minus k is perpendicular to 5i minus 4j plus 2k, which is correct. Now, so let's look at projection. Projection is another theorem of dot product. So, the scalar projection of B onto A, which is also called the component, of B along A, is defined to be the sign magnitude of the vector projection, which is the number. So B. So the scalar projection of B onto A, which is called the component of B along A, which is the number B, which is the modulus of B here, times the cos theta, where the theta is the angle between A and B. So the angle between A and B is the theta, and this is denoted by the symbol or clamp A, B. So this is how we write it. So B onto A is written in this form. So B onto A is written in clamp of A, then B, right? No, one thing you have to observe is that it is negative if pi on 2 is less than theta, also less than or equal to pi. And the equation there we are going to get is the dot product of A and B. The dot product of A and B should be equal to the modulus of A multiplying the modulus of B cos theta, which is also equal to the modulus of A multiplying into brackets the modulus of B cos theta. So this shows that the dot product of A and B can be interpreted as the length of A times the scalar projection of B onto A. Now, since B cos theta is equal to A, so the dot product of AB on the modulus of A. and this should be equal to A on the modulus of A dot B. Very simple. So the component of B along A can be written by taking the dot product of B with the unit vector in the direction of A. So we can summarize these ideas as the follow. So with the first one, with scalar projection of B onto A, we should have the comp of AB, which is equal to the dot product of AB over the modulus of A. So the scalar projection of B onto A is written in this form here. Very simple. And the second one that you need to take note of is when we have the vector projection of B onto A. So the first one, we have scalar projection of B onto A, and this one is vector projection of B onto A. So with this one, we should have something like the projection of B onto A should be equal to, open bracket here, so the dot product of A and B on the modulus of A, close bracket, then you multiply it with A on modulus of A, and when you do this, you should get A dot B on the modulus of A squared times A here, right? So just note that the vector projection is the scalar projection times the unit vector in the direction of A. So the vector projection, right, is equal to the scalar projection times the unit vector in the direction of A. So let's say if it was in the direction of B, then here is going to be B on the modulus of B. So but this one is in the direction of A, right? Very simple. Now let's take an example. So let's find the scalar projection and vector projection of this form. So example, so the vector projection, so let's write the vectors. So we have A being equal to -2, 3, then 1, then B being equal to 1, 1, 2. So let's find the scalar projection and vector projection of B onto A. So this one's gonna be in the direction of A, right? So first of all, we need to find the modulus of A. So the modulus of A here should be equal to 2 squared plus 3 squared plus 1 squared. And when we do it, we should get the root of 14, right? So that is the scalar projection of B onto A. So the scalar projection of B onto A is comp of B onto A equal to the dot product of AB on modulus of A. And when we do it, we should get -2 multiplying 1 plus 3 multiplying 1 plus 1 multiplying 2 on the root of 14. And when we do it, we should get 3 on root 14. So that is the scalar projection of B onto A. So B onto A. Very, very simple, right? Now, let's look at the vector projection, right? let's look at the vector projection. So with the vector projection, we already know the modulus of A, so we don't need to find it again. So with the vector projection, we should have, so that the vector projection, so vector projection, right? So that's gonna be proj B onto A. So the scalar projection, which we had 3 on 14, multiplying the unit vector of A in the direction of A. So multiplying A on modulus of A. And with this, we should get 3 multiplying root 14, right, times root 14, because we have the modulus of A, so times A. Then when we do it, we should get 3 on 14A. Very simple. And what is our A here? Our A here, we have our A. When we go back, we have our A to be negative 231. So we should do it. We should get the vector projection to be negative 3 on 7, 9 on 14, 3 on 14. And this is our vector projection. And this is the end of this video. I hope you like it. Like this video, and I'll see you in my next video. So there's subsequent videos that we are going to solve questions on all whatever we have done on algebra, from complex numbers and vectors. So keep out. If you are not solving a lot of examples, watch out. We are going to solve a lot of examples, a lot of examples in a different video altogether. So in that video, we are just going to solve examples of vectors and complex numbers. So watch out. Thank you for watching this video, and I'll see you in my next video. Bye.